Okay, hello 61C. Okay, so this is the first lecture from the second midterm, and we have a special lecture so that you can refresh you guys from the exam nightmare. So, okay, so this lecture is about warehouse scale computing, which is a kind of new stuff. So here today we are talking about a warehouse scale computer. So it's kind of a new computer. So it's giant and it's a giant computer. So you cannot imagine your life without this kind of computer because it makes it possible. It makes the internet services possible, like web search and social networking. And also from the software side, we are talking about two kinds of parallelism related with this kind of warehouse scale computer. One is request level parallelism, which is so you can see this parallelism in the web services, like in web searches, and also we are looking into a new kind of data level parallelism. So which is for the data, a huge amount of data set across multiple servers. So also this is relevant to your project flow. So project flow is coming. So I hope this will be helpful for your project here. Okay, so in the news, I noticed that this is very old news because it's in 2011. So, however, I believe that this is also meaningful for this lecture. So, by the way, so is anyone entered UC Berkeley before 2011? Is anyone? Oh, okay. So, in my case, I was a senior after my 2-year military service. So, yeah, I'm an old guy. Yeah. Anyways, so in 2011. So Google searched the power consumption of its data centers and announced that so search cost per day per person is the same as running a 60-watt bulb for 3 hours. It's a huge amount of power, right? So here's the question: is it worth it? Or why do you have to consume this amount of power for just searching something here? Okay, so let's uncover the secret here. So this is an example of a warehouse scale computer. So you can see, do you see something here? Yeah. What can you see here? Yeah, you can see some buildings here, right? And then you can see a river, and you can see a wide field, and you can see some hills. And so you notice that this is quite isolated, right? So let's zoom in. So still we only see some buildings here. Let's zoom in again. Then, okay, here you can see a building. So it turns out that it's a computer. Okay, believe me, this is a computer. So you can see some cooling system, a huge cooling system here. Okay, so let's go inside this computer. Then you can see some containers inside a building. Right? This is not very interesting. However, if you go inside this container, you can see kind of very fantastic picture. So this is there are some kind of blue or lights. I don't know what it is, but you can also see some wires connecting something here, right? And some lights from the machines, right? And then so let's see. So it actually turns out that those kind of things consist of just one unit of server. This is a server, And so we have another higher unit, which is called a rack. So it usually consists of some 32 to 64 servers or whatever. And there is another higher unit, which is called an array. So they are connected by their local networks. And then let's move into inside a server. So you can see CPUs here and DRAM and disks here, right? And this is a picture from another point of view, right? Okay, so here, let's define what's a warehouse scale computers, okay? So you can think of it as just a data center, which is a collection of 10,000 to 100,000 servers or more. So they are usually connected by its local networks. And however, this is not just a collection of multiple servers. It acts as a single gigantic machine, okay? So you can think of it as just a single computer, okay? So this is the main theme of this lecture, okay? So you can run a very large scale applications like internet services, including web search, email services, video sharing, and social networking. So this is usually always available, right? You cannot imagine that the situation where you cannot Google is not accessible, right? Over 30 minutes. So this is always available here. So because this is kind of a single machine, we can, so from a computer architect's viewpoint, we think that we can use the background on computer architecture to build efficient warehouse scale computers. So this is why we include warehouse scale computer in this class, okay? All right, so let's move on to, let's look at the uniqueness of this kind of new computers. Okay, so first thing is, so each application has a lot of parallelism, okay? One is, as I said, request level parallelism, like in web services. And then also there are data level parallelisms. So one example is image classifier training, so which is what you have to do for Project 4. And also this is a huge machine. Because of this, there is some opportunities, and also there are some problems here, okay? So you can see scale of economy. So because you can get low per unit cost here. And then for this reason, there is a new industry which is called cloud computing, so that you can rent computing power with low cost instead of having your own machines. But because of its scale, we have high number of failures in a warehouse scale computer. So, for example, if you assume that we have 4 disks per server, and its annual failure rate is 4%, okay? So in a warehouse scale computer of 50,000 servers, so there will be a 1 disk failure per hour. So that means if you don't have multiple copies of data, then you have to fix this failure every hour, right? So this is a kind of problem here. Also, unlike other kinds of computers, the operation cost matters here. So because its lifetime is longer than just other kinds of machines, because it's longer than 10 years. And so here, the cost of ownership is much, much greater than the cost of the machines themselves, okay? Then, okay, let's move on to the warehouse scale computer architecture. So we already have seen the features of a server and rack and array, okay? So in a server, we have 8 cores and 16 gigabyte DRAM and 4 1 terabyte disks. And as I said, a rack is a higher unit of a warehouse scale computers. So in a rack, we have 40 to 80 servers, and these servers are connected by cheap local Ethernet switches. And another bigger unit is called array or cluster. So it consists of 16 to 32 racks, and these are connected by expensive switches. So if you want to increase 10x bandwidth, then it means 100x across here. Okay, so then this is warehouse scale computers storage hierarchy. So it's very similar. It's somewhat some extension of memory hierarchy of a single machine. So you can see caches here and local DRAM and disk here. And outside of single server, you can see DRAM and disks in a rack. And outside this rack, you can also access DRAMs and disks in an array. So here, interesting is, so let's compare the access to the local disk and the access to DRAM outside a single server, okay? So here, so the latency to DRAM inside, the latency to a local disk is 10 milliseconds, and the latency to DRAM outside a server but inside a rack is 300 microseconds, which is much shorter. So from this, so it is much beneficial to have data on DRAM, right, across multiple servers. However, let's compare the bandwidth here. So the bandwidth of local disk is greater than the bandwidth of DRAM outside a server. That means the data transfer between outside one server is very expensive here. So so the software developer should be aware of this kind of fact, okay? So this is also a workload variation for warehouse scale computers. So you can imagine this kind of variation for like internet services, right? So it seems like access is increases here, right, after the midnight. So it's quite weird, I think, because I believe it should decrease after the midnight. I don't know what's happening here. Anyways, it continuously grows and then until at noon, and then it decreases again to the next midnight. So there are a lot of variation because bit usage is 2x up big. So you have to consider this kind of workload variation for to develop the software on a warehouse scale computer. Okay, so let's see. So for the software running, which is running on a warehouse scale computer, you have to consider latency and bandwidth of the memory hierarchy. Okay, so because this is related to the performance of your software. So usually, independent data set should be placed in an array. So you already have seen an array which consists of some multiple racks, and also locality of accesses within a server or even in a rack is very important because so data transfer among the data transfer outside a server is very expensive here. So you have a high failure rate on a warehouse scale computer. So this means this affects reliability and availability of the software. Okay, so here we may prevent failures, but it's kind of expensive because you have to, buy some expensive hardware. However, so the software should cope with these failures gracefully by having multiple copies of data. Also, we have to consider varying workloads, right? So this affects the availability of the software. So if there are a lot of contention, right, then so we have to anyways handle this kind of contention, right? So it should scale up and down gracefully according to varying workloads. So that means, by considering these facts, it turns out that developing the software for a warehouse scale computer is much challenging than just the software for a single computer. Okay? So here, power and energy efficiency is very important for a warehouse scale computer. Okay? That's because this is related to the operational cost. So this is directly related to money. Okay? So that's why we want to improve energy efficiency on a warehouse scale computer. So to measure energy efficiency, we introduced a new metric, which is called power usage effectiveness. So this is defined by total building power over IT equipment power. Okay. So this metric doesn't consider the efficiency of computing units, and if it's 1.0, then that means okay, this is perfect. So it turns out that the PUE of Google's warehouse scale computers is usually 1.2. So here, so this is the graph for the PUE of data centers in the world. So as you can see, some data center is efficient, right? If you see this, but something like this is very inefficient. So it's roughly 3, right? So more than 60% of the total energy is consumed elsewhere, right? Instead of consumed by the computing unit here. And the average is kind of 1.83. So as you can see, it's very inefficient, right? So then where the energy goes here? So we have the power breakdown for a warehouse scale computer. Okay, so only 30% of the total power is consumed by the computing unit here, and roughly 20% of the entire the total power is consumed by power supply system. It's a huge amount, right? And also, roughly 40% of the total power is consumed by cooling systems. This is a lot. So energy inefficiency usually comes from the cooling systems, right? So we have to design a warehouse scale computing to reduce this kind of overhead, right? So in fact, from a computer architect's viewpoint, we do almost nothing for these two parts. However, we may improve this kind of portion here. So you might think that this is not very meaningful, but it's not actually, because anyways, we can save money by improving this portion, okay? Also, cooling, so the heat cooling system is it's a little bit, so cooling systems have to deal with the heat produced by the computing unit, right? So by improving this portion, we may reduce this kind of cooling, the energy consumed by the cooling system. Okay, so let's talk about how we can improve the energy efficiency of the computing unit. Okay, so this is CPU utilization profile for a warehouse scale computer. So, what do you think we can conclude here? So, can you see anything from this graph here? Yeah, so, okay, this looks terrible, but okay, let me explain this graph, okay? So here, this means that, so CPU utilization is 0 here, right? So that means the server is idle. So usually, most of the time, the server spend in its idle status here, or the servers are only utilized from 20% to 60%. So it's not utilized fully. It's rarely utilized fully, as you can see here, right? So by using this fact, we have a new concept, which is energy proportional computing. So this should be the design goal of a warehouse scale computers. So, okay, this is somewhat complex here, but let me explain one by one here. So, okay, first we start from the fundamental equation, which is energy is equal to power times time, and energy efficiency is computation over energy. Okay, so that means energy efficiency is proportional to 1 over power and 1 over time. Okay, here, so the brown line, this shows typical power consumption from the servers. Okay, so as you can see, so it decreases linearly as the utilization goes down, right? And when it's idle, it consumes 50% of the power compared to the power. Okay, so when it's idle, the server consumes 50% of the power when it's fully utilized here, right? So it looks like it's very desirable because it consumes less power as its utilization goes down. However, from energy point of view, so this brown dashed line shows its energy efficiency here. So here, as I said, so the server spend most time in 20 to 60% of utilization here. However, this energy efficiency here is very poor. So we have to achieve some high efficiency here. So that means we have to, so the server should consume almost no power when it's idle. So this green line shows it linearly decreases, but when it's idle, it consumes only 10% of the entire power, okay? Then we can achieve much better energy efficiency here, okay? So further, if the power decreases sublinearly, okay, then we can achieve much better energy efficiency when the server is utilized from 20% to 60%. So this is what we have to achieve here. So this is the concept of energy proportional computing. However, in reality, it's hard to achieve this kind of thing here, right? So let's see why it's the case here. Okay, this shows the power breakdown according to CPU utilization. So if it's 100%, so CPU consumes 50% of the total power. And if it's idle, the CPU consumes 30% of the entire power, okay? However, if you see the peripherals like DRAM, disk, and other things, which includes network switches, and you can see that it doesn't decrease a lot as the server becomes idle, right? So this is what you have to improve to get energy proportional computing. So that means we have to improve, anyways, the energy efficiency of peripherals. So, however, this is a kind of very difficult problem. Also, it's an open-ended problem. So you can join the research to improve this efficiency, then to make the world better. Okay, then let's talk about cloud computing, which shows scale of economy here. So this table shows the price of each instance in Amazon EC2. So here, standard storage is almost comparable to the server in our example here. So as you can see, it's kind of very cheap, right? Surprisingly, Amazon makes a profit from with this low cost, right? This shows the scale of economy. So for the customers, it's better to rent this computing power from cloud computers, right? To just instead of just buying the machines, right? Okay, so any questions on warehouse scale computing?
What is the cloud? So, what is the cloud?
Cloud computing is like, it's also kind of a data center or a warehouse scale computer. So basically, you have a lot of multiple machines on a system, and then it can borrow the computing power, right, from these huge computers. Okay.
How is that different than the other warehouse computing?
So usually warehouse computing is like, so we want to run a huge application like web services, right? So this is another kind of services, right? So we can give some computing power to the users, right? So, but here the point is, this is very cheap, right? So in this case, it's better to rent this computing power instead of buying the machines, right? Okay, so then let's move on to another topic, which is request level parallelism. So request level parallelism exists because there are hundreds of thousands of requests in a very short time, okay? This doesn't occur on your laptops or your cell phones, but it occurs on like a warehouse scale computer, like running web services, right, including web search, social networking, and video sharing, right? So the point is, these requests are independent to one another, right? So imagine that you have search query, right? This is independent of your friend's search query, right? So also this usually involves with reading database. So you don't have to worry about something like a synchronization problem, like in the case of thread level parallelism. So that means computation can be easily partitioned, okay, across different requests and even in a single request, okay? So this is what Google Query serving architecture looks like. And here we have a Google Web Server. And then there are index servers having the information to handle the search queries. And then you also have document servers containing the information about the documents. And also on the side, you have a spell checker to check your typo. And then also an ad server to make a profit. Okay, so let's see. So if we Google cluster autonomous, you can see the results like this, okay? So you can see his homepage here, right? Yeah, and then you can see the project led by him. So this is Firebox, which is also related with today's lecture, which is about warehouse scale computing. And you can see some his talk videos here, right? So surprisingly, it's done. It takes less than 1 second, right? It's very fast. So let's see how it's possible here, okay? So if we Google cluster autonomous, then first, your query is sent to the closest Google warehouse scale computers, which is magically done by the DNS servers, which is a topic of network class. And then there is a server called front-end load balancer, which will send your request to one of many arrays. So this is the same as the unit, right? In the warehouse scale computer architecture, right? And then within this array, it selects one of many Google Web Servers, which are idle. And then this Google Web Server handle your request and return the result for your query. And then this server communicates with index servers containing the information to handle your query. And so it basically returns. So it returns the information to find the documents containing the keywords which are cluster and autonomous here. And then finally, it returns the document list ordered by the relevance scores. And then in parallel, so the server also communicates with ad systems because Google has to make a profit, right? And then it also fetches some videos of his talks, right? And then the index servers return document IDs to access the documents on document servers. And then finally, it composes the return page. So by getting the documents from the document servers, so but the list is ordered by the relevance score, and it also has sponsor links and advertisement to make a profit. Okay, so here's the implementation strategy for web search, okay? So first, we randomly distribute the entries of its keyword, right? And also make many copies of data, which is called replica. So this is very important here. And also we want to balance the request across these copies here. So here we have many copies of indices and documents for each keyword. So this is because first you want to break up some hot search keyword like Taylor Swift. And then also it wants to increase the opportunities for request level parallelism, because by having multiple copies, we can handle multiple requests of the same keyword, right? And also, we can make the system tolerant of failures, because we can recover some failure from another copy. Okay, so any questions on this? Okay, then administrivia. So project 3 is out. So it's convolutional neural cat working. So let's maximize cat per second here, okay? It's due the midnight Sunday. And also project 4 is coming. So please register your teams by midnight Saturday, okay? Okay, any questions about this? Okay, clicker time. Which statement is true among these? So did everyone finish it? It's not increasing now. Okay. Let's see. Oh, so. Okay, can you see the result here? Okay. Okay, there's one major answer here. Okay, I will give you another chance to get the right answer, okay? Let's start.
Whether you can remove the
Okay, let's see the result. Here. Okay, so still is the major selection. So so the answer is E. Okay, let's go over one by one here. Okay, so idle servers consume almost no power. So it's desirable, but in fact, it's very hard to achieve, right? So usually in the idle status, servers consume like roughly a half of power. And disks will fail once in 20 years, so failure is not a problem of WSC, a warehouse scale computer. It's not true, right? Even though its failure rate is very low, you have so many disks in or warehouse scale computers, so you can see almost one failure per hour. So you can handle this kind of high number of failures here. Also, the search requests to the same keyword from different users are not dependent. It's actually independent because we have multiple copies of data for each keyword, right? And warehouse scale computers are not good at batch processing. It's not true, right? So actually, it's very good at batch processing. So the next topic is related to this kind of thing here. And also, warehouse scale computers contain many copies of data. Yeah, this is the answer. So to improve parallelism and to cope with some high number of failures in the system. Okay, let's take a 2-minute break. Okay, so let's jump into data level parallelism on a warehouse scale computer. Okay. So we have already looked at data level parallelism in a single machine. So it's supported by, which is called SIMD. So it's basically supported by additional instruction and hardware in a single machine, right? So it's one of its applications is like matrix multiplication in a single memory, right? So now we are talking about data level parallelism in on warehouse scale computers. So this is kind of parallelism on a huge amount of data set, okay? So it's supported by MapReduce, which is kind of a framework to support this kind of parallelism. And also we need a scalable file systems to manage the files on multiple disks and also to cope with failures on of these disks. So one example is training deep convolutional neural networks with images across multiple disks. So that means it's your next project, and so this is useful information for the project here. Okay, so then what is MapReduce here? So MapReduce is first a programming model for data parallelism. Okay, and also it basically provides some the interface to the software developers, and also it's an implementation to support this interface. Okay. So from the interface perspective, we have two functions. One is map, and another is reduce. So we will talk about these two functions in detail very soon. Okay. From the implementation perspective, so there is a runtime system to automatically parallelize the computation across large scale of clusters of machines. Okay. Also, it has to handle the machine failures, and lastly, it has to schedule inter-machine communication because communication outside a server is very expensive. Okay. So if you are interested more in MapReduce, you can read this paper. So it's readable at the 61C level. So I recommend you read this paper. And so what is MapReduce used for then? So it's used in many places for various purposes. Okay. So like including index construction and spam detection and data mining or whatever. Okay. Okay, so then let's talk about MapReduce functions. First in Python. Okay. So first you want to calculate this equation. Okay, so this can be done by this Python code. So you can see map function and reduce function. Okay? So actually, this is done sequentially in Python, but you can do this in parallel. So let's see. So we have a data set here. Okay? Then map function applies this scale function, right, to its element inside this list. So then you can get the scale of its element, right, like this. Okay, and then next we have to reduce this data set by reduce function. So this reduce function applies this sum function to gather all data set. So first, we can reduce these two guys, right? And then we can get intermediate results. And then finally, we get the answer here. Okay? So by and MapReduce is actually, so by using map and reduce functions, you can specify the task which can be done in parallel on a warehouse scale computer. So first we have map function, so which gets input key and value pairs and produce the intermediate key and value pairs. Okay, so tasks are done in parallel by the map function, and it actually slices the data into a smaller chunk of data, which is called shards or splits, and then it distributes this data to worker servers. Okay, and then we have another function which is reduce, which gets the intermediate key and the list of the values related with this key. Okay, then it produces the list of alpha value, and then so this reduce function combines all intermediate values for each key. Okay, so this is not very clear to you now. So we have an example which is word counting in a document here. Okay, so for map phase, we have document name as an input key. Okay, and we have a document content as an output value, and then it will produce the list of word and count pairs. Okay, so if you see this, so if we have I do I run, right? So then we have a pair of word and count pairs, right? So there might be some duplicates. So this will be reduced by the reduce function. But now the map phase will generate this kind of pairs. Okay. So here in map, it actually generates for each word, it generates word and count value. So here this is the value for each word. So we are only looking at one word in map phase, right? So it generates a pair of word and just one here. However, in the reduce phase, we actually calculate the word count. So because for each word, we will get the count values, the count values generated by map phase, right? So we have some intermediate, we have a temporary variable to get the count, right? And then we eventually get the counts for each word in the document. Okay, any question about this? Okay, so then let's move on to how it's implemented, right, on a warehouse scale computer. Okay, so here you have a program, right, written in with MapReduce APIs, and then you have a master server to control the entire task. And then you have worker servers for map functions and reduce functions. And data is split into some smaller chunk of data, which are called splits. Okay. Then now here, so the data is split into smaller chunk of data. And then we start the execution of MapReduce. And then the master server controls the entire task. So it assigns map and reduce tasks to idle workers in a warehouse scale computer. And then, so we can do map tasks in parallel, right? So these map workers perform map tasks and generate intermediate key value pairs. And then they write the result to the buffers here. And then now it's time to reduce the data sets, right? And the reduce workers read intermediate key value pairs and sort them by its key. And then if maps are done, and then these reduce workers start its work. And so it reduces the data set for its key and then write the result to the alpha files. Okay? Any questions about this? Okay, so then we have looked at some general concept of MapReduce. And now, so for MapReduce, there are some example implementation which are available to you. So Hadoop is open source MapReduce framework. And so basically, it consists of two parts mainly. So it provides the file system which manages the files across multiple disks, okay? And also it produces, it provides MapReduce Java APIs, so you can implement MapReduce using in Java by using its interfaces, okay? However, it turns out that MapReduce is very low level and something like this. So there is another framework which is called Spark. So for the project, you will eventually use Spark, okay? So it's fast and general engine for large-scale data processing. So it's more than just map and reduce, but it provides some APIs for database, machine learning, and graph algorithms. So surprisingly, it's developed in the AMP lab at UC Berkeley. So now it's widely used by many other groups. Also, the thing is, it's running on Hadoop file systems, but it provides some kind of very clean APIs to the users. Okay? Now, this is MapReduce implementation. So this is a word count in Hadoop Java API. So it's very tedious to write down its MapReduce using Java APIs here, right? So in pseudocode, it was very simple, but it's now very tedious, right? It's very complex. So you have to, define map function and reduce functions here. And then you have to specify map function, explicitly specify map function and reduce functions to its Hadoop. And then it do something by using map and reduce implementation. Okay, so if you have to implement, if you have to do projects by using these APIs, then it's terrible, right? So thanks to Spark, it's very done cleanly, okay? So it's very short, right? Yeah. So, okay, let's see. So this is possible because, so here we load some data, right? So it's kind of so it's an abstraction. So it's an abstraction of a distributed collection of items. So which, on or across multiple disks or whatever. However, it's it acts as like a single data structure in Python. So you can use this data as if a single data structure and apply some related functions here, okay? So there are two kinds of operations for this data, okay, data set. So actions actually do get this data structure. This is called IDD, and generates a single value, okay? You carefully apply these action functions because in many cases you wanna reduce for each key, not the entire data set, right? So there's another kind of operations which is transformations. So which gets IDD as an input and generates another IDD, okay? So here flat map reduced by key transformations, okay? So before for map, it actually generates word and count pairs, right? So here we use flat map and map to generate these pairs, okay? And then we reduce, so by using reduce by key, we get the total counts for each word, okay? So this is very simple. And this is what so basically you will practice this Spark in the section and in the lab, and then finally you will use Spark for your project, okay? Any questions on Spark here? Okay, so it turns out it's simple. So do you know what's the difference between flat map and map here? Any ideas about this? So, okay, here's the explanation. So here, flat map for this one, right? So for this one, we are looking at each line of the document, okay? Then it's by using a split method, right? It actually generates a list, right? So if we do not use flat map, then it generates like just a list of lists, right? However, by using flat map, we flatten this list of lists and then get pairs of key and value. Okay, so this is why we use flat map here, and then you can use normally map to get you intermediate key and value pairs. Okay. Okay. Any questions? Okay, all right. So it finished earlier than I expected. So we have seen that warehouse scale computers, which is a new class of computer, and its characteristic is like its scalability. So it has its opportunity and have some problems related to its scale. So also, energy efficiency is very important in warehouse scale computer, and it also has high failure rate because we have a huge amount of machines inside a warehouse scale computers. And also, we are looking at we have looked at request level parallelism, which is naturally exists in web services like web search. And you also have looked at data level parallelism on a large data set So MapReduce is a framework to support this kind of data parallelism. Also, Hadoop and Spark is an example implementation. Okay, so for this case, I have some bonus slides for convolutional neural networks, which is highly related with your project, right? So for your project, you don't need to understand the details about this kind of background. However, I want to explain why we have these projects for this class, okay? Okay, so our project is like, okay, you want to identify cat, right? And so basically we have a function, we have basically inputs, which is just like images, right? And so from this function, you want to get some prediction, right? Whether it's a cat or not. And so this function is called the model, okay? So usually, in order to predict, we have to train this model. However, for project 3, we are only interested in just like optimizing the prediction, not the training. But however, for project 4, you will optimize the training of this model, okay? And you have also, basically, you are given data set. So this data set consists of its input, right? And also this is known output. So for example, we have a bunch of images, and so this data set we already know whether it's cat or not. It's given. However, you want to train the model to predict other kinds of images. So for training, we use this data set and then run the model, this function, right? And then so in training, we want to minimize the loss function. And so you are optimizing convolutional neural networks. So neural networks is an algorithm of machine learning. So its application is like digit recognition, speech recognition, image classification, or whatever. And here's a basic unit of neural networks. So it's called neuron. So to mimic the behavior of actual biological neuron. So here, this graph is kind of somewhat complex, but it actually, we get some inputs, right? And then we calculate the weighted sum of these inputs here. So each branch has its own weight, right? And then, so we apply some kind of function, which is called the activation function. So this is one kind of this function, which is called rectified linear unit. So by applying this kind of a nonlinear function, we believe that we can improve its accuracy. So it turns out that, so please note that it's actually, right? So weighted sum is actually a dot product here. Okay? So this is a small example of neural networks. So for its output, you have its functions here. But the point is, it turns out that it's actually doing matrix multiplication. Okay? So it's called general matrix multiply, which is abbreviated as GEM. So because of this, we can optimize, this neural networks very easily. So this convolutional neural networks is kind of neural networks, but it's somewhat different. But previously, the neurons are fully connected to each other. But in this case, we are looking at a local region of input image, okay? So here we have some local image, and we have a function called a corner to get some value from some relationship from this local region, and we eventually get the output like this, okay? So in project 3, actually the prediction function actually, looking at these local regions, and to multiply this input and corner, and you will get the output here. So it turns out that convolutional neural networks can be transformed into matrix multiply. So you have images here, and you have a bunch of filters, and then you can make this local region to a bigger matrix, and then we can also pile the filters to get a bigger matrix here. So actually, in project 4, we actually do this kind of thing to get so that it can just view as matrix multiply. And then so the problem is here we have multiple layers for this system. So you have a bunch of layers, and this is why it's called deep convolutional neural networks. So there's no theoretical background to have many layers, but empirically it's known that it's improving its accuracy. However, that means it's kind of it requires a lot of computation. So that's why we want to optimize deep CNNs to make it feasible for the users. Okay. So then, why we have deep CNNs for the projects here? Okay, so deep CNNs are recently an emerging machine learning algorithm. So it's a very popular one, right? And so it turns out that deep CNNs are equivalent to GEM, which is just matrix multiply, right? So also you have to notice that there are a huge amount of parallelism because images are independent to one another, right? And you have to notice that you already have skills to optimize matrix multiply, right? Because you can do cache blocking, vectorize this matrix multiply with SIMD instructions, and thread level parallelism with OpenMP. And finally, you will use MapReduce and Spark to optimize deep CNNs. Okay? Okay, so the question is, do we have to use Spark to MapReduce in Spark for project 4? You can use other functions, right? If you get the correct result and fast result, you can get the result fast, right? So as I explained, Spark is more than just MapReduce. It provides various functions you can manipulate, right? Okay, any other question? Okay, no questions? Okay, let's call it a day. See you on Thursday. Thank you.